Hello, hello. Oh, yes, it works. Yeah, I have about 2 hours worth of content that I'm going to try and do in 45 minutes. It's all going to be okay. I guess the reason why I have so much content is because we're talking about TLS, and it's usually something that we don't, as web developers, tend to deal with. But given the audience, you might deal with it a lot. We'll go ahead and see. So I'm Natasha Rooney. I'm the web technologist at GSMA. It's a bit of a misdemeanor, really. I'm actually a web and internet technologist. It means I talk and know a lot about web and internet, tend to not to work with it as much as I did previously. I was a web developer at one time and a Java developer a long time ago. We won't talk about that. So we've got lots and lots of stuff to talk about today. And these are some of the things I want to discuss in this talk. We're going to take a quick look at public key crypto because it's so important to TLS, some history for TLS. We're going to mostly look at how TLS 1.2 works, talk a little about round trip times, how to configure TLS so that it works a little bit nicer or not. Some of the work happening in TLS 1.3 and new bits and pieces with certs, and then I've got some references to throw in there as well. So why do I need SSL or TLS, or why do I need to upgrade my site to HTTPS? If you need to ask this question, you probably haven't been following things recently. Given a lot of you guys are regular attendees of this group, you probably understand this quite a lot. This is a slide that I actually took from another slide deck that I have about identities. A lot of stuff going on in identity in the web right now. And this is just to say that data breaches can have a real and significant impact on a number of businesses. And it's not just your own business that you need to be worried about, or the businesses that you look after and that you code for, but also for others. Most of the time, users reuse passwords. So if you want to go ahead and manage any kind of passwords on your site, if you're not doing that securely, you're putting those users in jeopardy. Also, if you're holding any thing that might be deemed sensitive in this country, but also in other countries. One of my famous stories about this is Facebook kind of stepped up a lot of their content to be HTTPS once they learned that some governments in some African countries were snooping on their users to find out whether they were looking at information on homosexuality and then going ahead and persecuting those people. So some things that don't seem to be necessary to upgrade for reasons to upgrade to HTTPS, there are actually real, large benefits to upgrading and going down that path. So as I said, I wanted to do a quick intro to public key cryptography. I really like Pokemon, so it's a lot of Pokemon in a lot of my slides. I'm really sorry, it's a thing. And I'm going to explain public key cryptography without looking at Alice and Bob. We've got Jesse and James here. So let's say, for instance, Jesse wants to go ahead and send a message to James that says, "Let's get that Pikachu." Traditional cryptographic methods, we use symmetric cryptography, and as you can see by the diagram there, we've got the letter B and we're going to encrypt it to become the letter E. We do that by shifting it over 3 spaces. So the key in this algorithm is 3. This is a Caesar cipher, a simple cipher. So Jessie encodes her message, "Let's get that Pikachu." It's the blue message, you can see below that. And she has a key, she encrypts the key that's 3 as well. Now, James doesn't know what the key is, so with the message, she must also send the key. So she sends the key and the message to James, who's able to go ahead and unencrypt it. But what if Pikachu is sitting on the line? Pikachu can see this message, he can hit the encrypted message, and he can see the key, which means that he's able to go ahead and unencrypt the message, and he understands it. It says, "Let's get that Pikachu." Now, asymmetric cryptography works a little bit different. You actually have 2 keys in this scenario. You have one secret key that you keep to yourself, and then you have a public key which you go ahead and share with others. So James is the one with the keys in this particular scenario. Usually both have keys, but we're going to go with James. James has a private key that he keeps with him. It's that gold key alongside him. And the silver key, the public key, he sends over to Jessie. So Jessie takes her message. She uses the public key to encrypt it, which is some stream of bytes that gets sent over to James. James uses his private key to go ahead and unencrypt it. Sometimes it's very difficult to understand how a private and public key system can work in this way. How can a cryptographic method not be reversible? The best example I've heard of this being explained is a bit like creating colors. If you take some shade of red and some shade of blue, you know it's going to make some shade of purple. But reversing that purple to create that blue and that red again is near enough impossible. And this is maths is akin to that. So if Pikachu's sitting on the wire, he'll get the public key and he'll get the encrypted message, but he's not able to do anything with that. So he's pretty peeved. So James is kind of happy, yay, good for him. The big question is with PKI is, does this really, you need to know if this public key really belongs to James. A hacker could have sat in the middle and sent you a public key pretending that it was James when you didn't actually know. And this is when certs come in. So certificates, to get a certificate, James would have contacted or reached out to a certificate authority who would have then gone ahead and checked James's identity. A number of famous ones are DigiCert and VeriSign, but there are a lot of certificate authorities. And in fact, anyone can be a certificate authority, which is another set of issues. Certificates mostly are in the X509 standard. It's an ITU standard. You can look it up if you want some fun reading or some quick method to go to sleep. So James will go ahead and send his public key. Now Jesse will go ahead and check the public key and the certificate that came along with it with the Giant Meow Certificate Authority, which is totally legit, and then know that James is exactly who he says that he is. Then this whole flow can go ahead. Now, incidentally, public key cryptography is used in a number of cases in SSL and TLS. In TLS, weirdly, it's not used in the actual encryption section, but it is used to set up all of the keys. So let's have a little bit of a history lesson. So not all web developers understand the OSI model. It depends what kind of background you come from, but this is a refresher, I guess, from a lot of people. So the OSI model is a model of networking. A lot of us are very acquainted with the application layer at the top, which is all the HTTP stuff. But then lower down from that, packets are packaged up and up until we get all the way down to the physical layer, which is actually the cables that connect routers to routers, boxes to boxes, and whatever. HTTP usually runs on TCP, which is on the transport layer on layer 4. Session and connection management at layer 3 manages all of the session stuff. And the layer that we're interested in here is layer 6, which is a presentation layer where SSL and TLS sit. So it sits in between HTTP and TCP. So we're packaging up HTTP packets and then sending them down to the transport layer. Now, SSL version 1 was actually developed at Netscape a long time ago. And it was pretty crappy, so they upgraded it pretty quickly to SSL version 2 and then included that in Netscape Navigator. This is all still Netscape doing this work. That was also pretty poor when it came to security, so they upgraded it in 1 year in 1995 to SSL 3. But although you can pretty much do this if you are a private organization. Now, TLS is actually the same, is just an evolution of SSL. The renaming mostly came because the SSL responsibility left Netscape and started to be worked on within the IETF in the TLS working group. Now, when that all started, Microsoft and Netscape had a number of arguments, let's say, discussions, which halted TLS 1.1 from really being standardized until 1999. It's 3 years. I mean, it's standards, that happens. TLS version 1 was pretty good, but it had a number of hard-coded elements. So it couldn't really, it wasn't really extensible enough to continue to keep up with the security that was needed. So after a number of security fixes in 2006, the group actually worked on developing TLS 1.2, which mostly is what we use today. TLS 1.2 is much more configurable and flexible. We'll look into that in a bit. It's a nice screenshot of the TLS version 1 spec from 1999. So TLS has a few aims. It tries to keep things cryptographically secure between two parties. It wants that to be interoperable across the internet. It needs to be extensible, as I said, but it still needs to be efficient. And so we'll look at that and how that's evolving later. I like to say that TLS, makes you not have a TIFF. You don't want to have any message tampering, message interception, or message forgery. So clearly, those are the aims that it tries to reach to. Now, TLS can actually be very nicely divided into 3 separate sections and how it works. You've got this handshake, which includes the authentication and key exchange. And then you've got the data exchange, the actual data of the application data that you're trying to send over and receive. And then the shutdown, so when all the connections are done. And yes, that does take some time. So like I said, let's take a look at TLS 1.2. Now, the handshake actually has about 6 to 10 messages that it sends back and forth. This doesn't mean that it has a lot of round trips. We're going to have a look at how many round trips it has, but it's those things that are going back and forth. It'll exchange capabilities and agree on parameters and set those things. I actually have a better way of looking at it. It's on the next slide, but it's really, really small. I like some of the slides to be very useful at a later date. So I know this isn't a very good slide for presenting to you guys, but hopefully it'll be a good slide as a reference at a later point. And the reason why I created this was because the actual TLS handshake flow, which looks like this, explains nicely how things go back and forth, but not actually what the client and server are doing with those pieces of work. So if you look on the handshake flow, I'll talk through it, it's a little bit easier. In a client's hello, the client will send a set of ciphers that it wants to go ahead and work with, and it actually shows like this thing down here. It will send a number of these ciphers that it wants to go ahead and work with. And I wanted to create this slide because there's not just one cipher in TLS, there's a lot of ciphers, and so understanding that is quite difficult. So we have actually it's easier for me to read that because I can't read that from here. So client sends its TLS versions, its cipher suites, and its compression methods. And the server will look at that and respond with the one that it wants to go ahead and use. So the client sends a list of ones that it quite likes. I think I have a screenshot here of it. Yeah, cool. So this is Wireshark. It allows me to sniff on certain ports. I was having a look for good examples of client hello, and this is actually a client hello from a Chrome browser over to Wikipedia, and you can see the cipher suites that my Chrome browser is happy to go ahead and use for this particular case, and Wikipedia's server will select one that it wants to use, and then we'll start to continue with the handshake. So the server selects a cipher and a compression method, and at the same time, it will send back a certificate, which the client can then go ahead and authenticate. Now, the authentication methods uses a bunch of cryptographic algorithms as well. They are things like RSA or ECDSA. RSA is probably something you've heard that's not so quite as good as anything with an EC in front of it. That usually stands for elliptic curve. In fact, it's still very much in use for a number of reasons. Now, given the data that the server has sent back, the client can go ahead and create and work on the key exchange. Now, the key exchange helps to create a pre-master secret. Now, the pre-master secret is exchanged between the client and the server so that they can both create a master secret. I know this sounds very crazy. The idea is that with data that the client has, it can package up a pre-master secret and send that to the server. With those 2 pieces of information and previous bits of information, they create master secrets so they can symmetrically encrypt and send data to each other. This takes some time. We'll go through the actual flow because that might be helpful for other people. What also gets sent along is a MAC. A server verifies this MAC code, this MAC, and returns it to the client. Our MAC is here. We've got SHA-256 that we're using. This MAC allows us to verify the stuff that happened in the handshake. So what we want to do is to say if a hacker was sitting on the handshake and did anything to the handshake during the time that we were going back and forth and modified any of that, the MAC should show us somewhere that actually went ahead and happened. It's just a validation check. So the other thing this slide does, like I said, is show all of the different ciphers that's used for the different methods. This is actually a pretty good one that we're using, and we'll see for some time how that actually happens. So again, I'll just step through it. It's a little bit complicated, but we'll have the client hello. So the client sends all the TLS versions, cipher suites, and compression methods. The server will select all those connection parameters, and then the server will send its certificate chain as well. The server may send more information depending on what key exchange is particularly needed. So the client will send some more information to generate the master secret. And then the client switches to encryption and goes ahead and tells the server. The server will also switch to encryption and on the finished message tell the client. And the MAC will then be used to validate that as well. Cool. So that's the TLS handshake as TLS 1.2. There's 2 round trips there and a little bit of CPU. That's, I say a lot of CPU, but there is some CPU, but we'll talk about that a little bit later. The abbreviated handshake happens in the case where a user comes back to the website. So the first handshake should really happen only once a user goes to the website, or user accesses the resource on the first time. When the user goes back and accesses again, an abbreviated handshake or access a connection, an abbreviated handshake should happen. And this happens because a client and a server keep certain security parameters from the previous connection. So at the end of the handshake, some parameters are exchanged. This is called the session ID. And the client and the server keep a copy of this so that they can do an abbreviated handshake the next time around. The client will send its session ID in the client hello of the next handshake to the next connection. And then the server would then use this to go ahead and set up the connection using the previously defined master secret from the original handshake. Sometimes a client will send multiple session IDs and the server actually chooses out of one of them if such a thing has happened to occur. So you can see here again, the client sends the information with the session ID, the server sees the session ID, picks up a master secret that it has in store from the original previous connection, goes ahead and uses that to encrypt data and sends it on. So now we're down to 1 round trip, which is, a lot nicer. That's fun. Now, I've done a little bit more information on key exchange if people are particularly interested, why some keys are better than others. RSA is kind of rubbish on the key exchange. It doesn't have any forward secrecy, so if an attacker gets hold of it, they tend to be able to go ahead and unencrypt stuff that's happened by using information from previous sessions. Diffie-Hellman exchange is very good cryptography in strength, but it's also incredibly slow. Any of the elliptic curve Diffie-Hellman stuff tends to be quite quick. We've got some data showing that a little bit later on. I will move forward. Just on the note on encryption, AES tends to be our most popular cipher, and there are different versions of encryption. I've got a good example of this happening in the next slide. We have, in terms of encrypting the actual content after the handshake is completed, you're going to go ahead and encrypt that content. And if you remember back to our cheat sheet slide, let's go back. We have our encrypted cipher down here. AES128GCM is the one that we're going to be using to encrypt our actual content. AES is an AEAD type of encryption, so it's an authenticated encryption. AEAD stands for authenticated encryption with associated data. And it does something a little bit like this. It'll take a sequence number and a header, encrypt the plain text with those two, and then put that into a packet to be sent on into the TLS record protocol, which then goes ahead, packages it, and put them into the TCP. Oh, I had it right there. I didn't need to jump all the way back. So like I said, I built this nice little slide here to show all the encryption algorithms that I use in all the different methods, and I was upset to find the TLS 1.3 author of 1.2, Eric Frescola, actually did this in a nice simple slide showing key exchange, authentication, encryption, and MAC. But oh well, never mind. Mine's got some more information there. Now, finally, when we go ahead and send this over, everything gets packaged into this TLS record that has a header and data before it gets packaged into a TCP packet. It's a nice little flow here from somewhere I found, which I'll skip over because we have lots of stuff to go and do. Renegotiation is a bit of a pain in the butt. It's something that can often happen on TCP connections, on TLS connections, possibly because one of the sides wants to renegotiate the authentication terms, or they want to go ahead and ask a client for authentication as well as the server. It's actually found that the way it's implemented is unsafe, so it's probably better to turn it off if you still have it on. Okay, so that's fun, that's TLS. But weren't we here to talk about performance? Yes, we were. So I a lot of this information and a lot of the work that where I find out a lot about my stuff with TLS all comes from Ivan Ristic, which is a great guy who writes a lot of stuff about TLS and security and other such things. And even he wrote in his book about TLS and SSL that people sometimes care about security, but they always care about speed. And no one ever wanted their website to be slower. I actually think that people probably should care a little bit more about security, but that's generally me. Okay, so on the network, this isn't actually true of actual computers because obviously you've got this other element of CPU, but at least on the network, you've got two big problems when it comes to performance. You've got bandwidth and you've got latency. Now, weirdly enough, if you have a lot of money, bandwidth is actually something that you can go ahead and buy. If you're a large company and you need a lot of bandwidth, you're getting a lot of hits, you can go ahead and do those things. You've got cash, you can get it. Latency is a little bit harder. There's a number of things which we still have to get through latency, including if you're on a mobile network, getting a connection to the mast, waking your phone up from being idle, going ahead and transferring to your ISP, and then going over the transatlantic cables and whatever else. There's some good stats out there on mobile networks and other statistics. On 3G, it takes somewhere between 100 to 500 milliseconds latency to get to the base station, and that's only if your phone is woken up from idle. There's a weird way that it goes ahead and does that, which Ilya describes nicely in his book. In 4G, it's less than 100 milliseconds. That probably means it's somewhere around the 50, 60 mark, but it very much depends on the situation and where you are, and also what 4G means where you live. Otherwise, you can get probably about 100 megabits a second if you're stationary on 4G. If you're close to the mast and there's nobody else around, good luck with that. Waking from idle can take 100 milliseconds. And then if you are trying to grab something from a server that's way over in the other side of the Earth, transatlantic cables are about 99.7% the speed of light, but the speed of light is the speed of light. You can't get faster than that. And they do have a latency of also less than 100 milliseconds. But given the private transatlantic cables are around 60 milliseconds, you're probably still going to be getting around 70 or 80. So Mark Nottingham, who does a lot of work on HTTP standardization, he chairs the HTTP group at IETF, wrote a really cool blog post on how to improve HTTP performance. And we're going to look at how TLS is impacted in the same way. So first of all, he describes that, of course, HTTP sits on top of TCP. Now, this is a TCP handshake. It's different from what we've seen before. We have SYN and ACKs, and we all understand those. So we say, hello, server, and the server says, cool, hi, I can see you. And you say, here, here's some parameters. And we say, cool, there's my parameters. And we start to talk, and we go ahead and request a page. Now, oh, sorry about the font there. TCP fast open tries to do something, tries to make this a little quicker by sending the cookie and the get in the first request, and then going ahead and sending, the server then sends a SYN and an ACK and a data back as well. This needs to happen on a second lookup, I think, too. Now, if we add the TCP handshake well, of course it has to happen on a second lookup. There's a cookie in there. Sorry. Thoughts. If we add the TCP handshake and TLS 1.2's handshake, first visit, not any resumption visits, the first visits, we've got here a couple of round trips of the TCP handshake and a couple of round trips for the TLS handshake. So we've got 4 round trips, which isn't good if we're going to the other side of the Earth. And then if we do TCP on a fast open, because we're going back to the connection after another time, back to the same server. So we've got cookies there, and we can reassign, so we can do fast open. Then we add with a session ticket, so the abbreviated handshake. We've then actually reduced our 4 round trip times down to 2. Yay, that's pretty good. But we still have this massive problem of latency. We all know that round trip times are evil because of how many transatlantic cables there are, and how crap or good the mobile network is. And it doesn't really matter about how good all of that stuff is, because you still got to traverse all those things and cope with all those latencies. So everybody's very happy about you spending ages looking at the spinny thing on your phone. If you want to go ahead and start to make this easier, one thing that you could do is optimize TCP. So I know this isn't optimizing TLS, but one thing you can do to solve this issue is optimize TCP. Now, TCP's main issue is a lot of its congestion control stuff is kind of sucky. It's not its fault. It's just, it's very difficult to solve this problem. Because TCP tends not to understand what the networks out there that it's going to traverse over looks like, it can't make any judgments. So it can't go ahead and send large packets of data because it doesn't know if those large packets of data are going to be dropped. What it does instead is it starts to send small packets of data. And if it receives acknowledgements for those, it exponentially increases that those packets of data until, that amount of data until it doesn't receive one back. So we call this a congestion window. So the congestion window will get bigger and bigger, and we'll send larger and larger amounts of packets over to a server until we don't receive an acknowledgement back. Once we don't get an acknowledgement back, we halve that amount that we are sending, and then we start linearly increasing. And this is what creates the TCP sawtooth. If you look at the data over a long time, it sort of gets a little bit of a sawtooth. So there's bits that you can go ahead and do for optimizing TCP. You could go ahead and adjust your initial congestion window so it's larger. The problem is if your users are sat on networks which are kind of ropey, then it tends to be that they're going to have a really crappy time because they can't get anything. But one of the very interesting things that you can do is stop TCP from restarting so quickly. So if you've got a site where users are clicking on a link and perhaps they're waiting for a good few seconds before they click a link again, you could go ahead and keep your TCP connections open by using HTTP keep alive headers. Now, this would allow you to go ahead and keep connections open for a longer amount of time than perhaps 1 second it is in certain cases. Now, actually, in some of the browsers right now, they try to keep the connections open for a significant amount of time. It depends on the situation that you have, although it does seem 60 seconds is a good one to go and test on. The big problem is if you keep connections open for 60 seconds, you then mean that other people that are trying to access your server might get blocked really quickly. So if you have a number of concurrent users, you might not want to go and do this. So initially, I did say on this slide, you must tune server. And I really want to emphasize that you can if you want to, but you need to accept that it's not a hard and fast rule. This isn't just a Z transform 0 issue. So you can't control what browsers users use. Perhaps new standards will be able to help in this way. TLS Full Start was actually a Google project in this area which tried to reduce the number of round trip times again by sending data in the first client hello. It's sort of mildly encrypted using past encryption data. It did reduce latency down by 30%, but it was incredibly dangerous because that data sat on the client hello was very susceptible to being attacked. Google did declare it as a failure, but it is still in use in a lot of places. I think OS X 10.9 still uses it. Speedy was using it at one point, and Firefox 28 used it. I know that's a long time ago. Basically, it doesn't have forward secrecy, so it's not able to go ahead and the information's able to go ahead and be reused by a hacker to break that information on the first loop. Now, Speedy, HTTP, and Quick have also done some work to help here. They obviously were working on trying to make the web faster. Speedy also started to put encryption into the protocol and it needed to, mostly because the web wasn't, the way that the internet was working when Google started to work on Speedy, it was failing because it was hitting too many firewalls. So Google put Speedy over a TLS tunnel so that it was able to go ahead and start playing around with it. HTTP2 has opportunistic encryption, which you can turn on your deployment so that it has encryption built in. It's not very secure, but it does something against pervasive monitoring. And Quick actually has encryption built in. It's actually interesting, when I was looking at Wireshark, I found a number of Quick packets, but we know this. We know if you're using Chrome or Google products, and we know they've turned Quick on for some time, so there's no reason why I shouldn't be seeing lots of Quick packets. It is funny, though, they still say HTTPS in the browser, and it's technically not HTTPS. I still don't like that. It really bugs me. Okay, but these are all really great, but we're still, not exactly scratching the surface when it comes to, we are scratching the surface when it comes to latency. But there's one very easy thing that everyone can do to solve on latency issues, which will probably be way better than doing anything to TLS, which is installing a CDN. So CDNs obviously cache content closer to the user. They can also do a couple of other things, such as optimizing traffic and managing connections. This is really a first way to go if you're having a lot of issues on latency. They really can, CDN work can benefit any kind of TLS tuning, but it's fun to know about what we can do with TLS. CDNs is kind of one of these things I call throwing money solutions, doing things like CDNs, bigger server or server clusters. It's a chop money at it and it will go away. But you should have a look at it. And you can get a lot of CDNs services for quite a reasonable price now. So that's cool, but what can we do with TLS? Cryptographic operations, cryptographically encrypting every single packet that you're sending over the wire does take some CPU time. On the key exchange, we have some things that eat away at CPU time, including the, choosing the server algorithm. The key size is obviously an issue. If you choose an algorithm with a huge key size, the bigger the key size you're choosing, the greater your security, great. But the harder the CPU needs to work to encrypt everything, which is very, very hard. RSA now is actually, even though it was very fast in the beginning, is now actually too slow compared to some of the newer cryptographic methods, which are better anyway. So even though RSA, people feel like they still should be using RSA. If you're using ECDSA, that's the equivalent to using a 3072-bit RSA key, and it's better performance. So it kind of makes sense to go ahead and do that. Ecliptic curve Diffie-Hellman exchange is actually harder to predict how performant it's going to be, mostly because in the key exchange you will select a curve to go ahead and use, and because of that, the selection of the curve has certain impacts on performance. We do have some statistics to show us. It's very tiny. I'll walk through it because it's easier for me to do that. These are up at the top, we have the ecliptic curve exchange methods and the ecliptic curve algorithms. You can see how much smaller they are than most other things. Here we have a Diffie-Hellman exchange. So as I said earlier, Diffie-Hellman exchanges are really, really cryptographically secure, not as good as ecliptic curve, but they're in terms of CPU time that you're wasting, it's not worth it. And these ones down here have some kind of RSA. I think they have RSA on the key or on the algorithm, and they are faster, but they're nowhere near as faster as the ECDSA and ECDHE. So it's not really a competition anymore as it was perhaps at some time ago. Certificates also offer some ways to go ahead and improve on performance. And not many people understand them, so it's kind of a good thing to go have a look at. If you're sending certificates in your TLS handshake, you should only be sending the certificates which you need to send. And that's usually around 2. It's kind of your own certificate, and then not the root certificate, but a certificate that identifies your CA. Yes?
Sorry to interrupt. What if you're using big sans sets?
Big what, sorry?
Sans sets.
Oh, big sans sets. Sorry, what's a big sans set?
Subject of service name, where you get multiple host names.
Oh, okay. I did need to get that. I didn't know that was what it's called. The advice was not to use big host names.
Just don't do it.
Didn't know that was what it was referred to. Thank you. Not to use too many. I'll keep going through. The ECDSA sets are smaller, but yeah, it was not to use too many host names on one cert. I do have some notes about that. Maybe I'll go through it. Apparently, people do this because sites share the same IP address, right? So sites that don't, and these also seems to be sites that maybe don't support SNI. I don't know if they don't use SNI. So every single host name increases the certificate size, so that's kind of a problem. I don't know what your options are there. I guess your options are make a couple of certificates for each one or use the biggest one, but if you could decrease it, then that kind of would be better. I think we get to this at a later point, but your big problem with very, very large certs is you might force another TCP. Well, you might force another round trip time because the certificate is so large that then when it goes down to TCP, it has to be divided up into more TCP packets, and then you get even more problems. So if you're blocking at that time, it might be because of that issue. When certificates live out their lifetime, this is probably more when they have an impact, they do need to be revoked, and the browser needs to understand when a certificate is broken, and I'm really, really guilty of this. Revocation checking tends to happen in two ways. It's either through a certificate revocation list or using the online certificate status protocol. Browsers go ahead and request certificate revocation lists from certificate authorities, or they use the OSCP protocol to interact with the authority and get that certificate revocation information. Depending on when your timeout, how long your timeout is, it could be that your client is asking to get this certificate revocation list. It could be up to 10 seconds to go ahead and get it. When you're looking at a certificate authority, you really want to be checking that their revocation responses or their responses to their OSCP requests are actually very, very few. It might be that when you get to a point that your certificates are changing, that your users are just sat there trying to understand which certs they have and whether they're still valid or not. And that can be kind of crappy if you're updating a lot because you need a very secure site. OSCP stapling can help here as well. OSCP stapling is something that you can add to the TLS handshake. Now, OSCP stapling adds about 450 bytes to the TLS handshake. It's some data that then the client can go ahead and use to find the revocation information quicker. So it does add that extra bit to the handshake, but it means that the lookup on that information is much faster. So again, if you're changing certificates regularly, you might want to use OSCP stapling so that you can go ahead and decrease that latency for your users. Just on some note, if you have EV certs on your site, they will always check for revocation. DV certs don't, so most of us who have a small crappy site, it will be a DV cert. EV certs will check every single time. Do I want to go through session resumption? Just a quick note on session resumption then. Session resumption, it depends again on how much security you think your site is going to require. It might be quite adequate for a number of sites to do session resumption once per day. So you can set some of your session resumption figures so that they're one per day rather than asking users to re-sign up every hour or something, or re-establish a complete connection every hour. So the worst is over once the handshake finishes, mostly. But one kind of thing which is quite nice to know is the transport overhead of TLS. So how many bytes does it actually add when we're encrypting content, when we're past the handshake and we're going ahead and we're sending encrypted content back for each other? Now, the example that we had on our TLS cheat sheet was this one, third one down, AES 128 GCM SHA-256. So in this, using this particular cipher, we are going ahead and adding 29 bytes to every TLS packet that we're going to be sending, 29 bytes. So you're like, okay, that's kind of a lot, like 29 bytes. I don't really want to be sending that with every single packet. Oddly, TCP will probably go ahead and divide up, will fragment TLS packets to fit them into TCP packets. TLS packets tend to be at a maximum around 16 kilobits. Yeah, that's 16 kilobits. Yeah, that sounds about right. 16 kilobytes, sorry. And so they can go ahead and get about 16 kilobytes worth of data in a TLS packet. TCP tends to be set at around about 1/400, I think, something like that bit. Sorry. So every TLS packet is divided up into lots of different TCP packets, depending on how big a number of other factors are. And then what you find is that at that level, about 52 bytes are then added onto the TCP IP packet as headers and other such information. So then you see that your 29 bytes that you're adding at the TLS level isn't actually that much when you're going ahead and adding 52 bytes to every single TCP packet. In fact, the IETF don't seem to think that this is much of an issue because IPv6 adds 72 bytes. So if they don't think it's so much of an issue to create a more robust platform, which is adding 72 bytes for TLS certain fragments, then 29 bytes for us really shouldn't be that much of an issue. So this is just showcasing some TLS ciphers and the amount of time that they take on the CPU. This one at the top, I know you can't read it, is the old 3DS cipher, which 3DES cipher, which was in use for some time. It lingered on for a very long time because IE6 actually relied on it. Yay, thanks IE6 again. And further down here, we have the AES combinations, and right at the bottom, we have the AES 256. But this yellow one here is the AES 128, the SHA that we were using here. So we can see that these are very, very performant, and we're very happy with them. We don't need to do anything. It's all very nice. The only thing is not all mobile devices run AES or hardware accelerated AES. Didn't talk about too much about hardware acceleration. iOS does, which is nice. But not all mobile devices can handle that kind of CPU activity, and in which cases there was a piece of work that Google were doing on an algorithm called Char Poly 1305 to build a cipher which was which was twice as performant as AES, but smaller for mobile devices. And this update is about a year old, so we might have some more information there. Oh, this is a nice little diagram of our application payload and our TLS records on all our TCP packets. They're in the wrong place. The other issue we have is around buffering latency. So as we said, all our TLS packets go into TCP packets, and then we need to send them over the wire. TCP is a reliable protocol. It wants to go ahead and receive packets and then put them back in order for the higher levels. If we receive packets out of order, and we will because packets take different routes around the internet, TCP will wait until it gets those in. So you've got a bit of buffering there that you need to go ahead and play around with. TCP may have to recover some packets as well, and it will because of the way that its congestion works. So you're going to be working to that too. You could help with TLS by doing some tuning. This means you could try and find a way where your TLS records fit exactly within your TCP packet sizes. It's very hard to go ahead and do this, but if this level of performance is what you want, you could go ahead and start turning down your TLS record size from 16 kilobits, which is probably what it's set at, down to something like 4 kilobits. You can try. The better thing to do is to try and leave this to the web servers. Web servers tend to go ahead out of the box and discover the maximum transmission units, the MTUs. A maximum transmission unit is, we use it a lot in mobile land, is the maximum unit that we can go ahead and send over a network. They will vary the record then according to the connection and the types of information they're getting back on the connection. So it's probably better if you just leave them to do their job. But if you want to have some fun, you could go ahead and turn it down. Right, I wanted to say a little bit story about CPU time inequality, actually. It's quite interesting. I read this story in Ivan's book. RSA can actually be used to DOS if you want it to do a denial of service attacks. If you want to have fun doing that, don't do that. But you could. It's RSA actually, the client, when you have a communication between the client and server using RSA is actually harder on the server than it is on the client. It requires the server to do more things than it does the client. And so because of that, if you have one client which is sending loads and loads of handshake requests over to a server, you theoretically can do that and get the server to work very hard to try ahead and go ahead and do those things. And a number of these instances happen, and this was some presentation at DEF CON to show this thing going on, and that it's a big issue. And it was replicated and a patch was sent out and all this other stuff. ECDHE and ECDSA clients will do 1.5 times more work than the server. This is not a big deal. We can afford it. We're only sending so many connections whilst the server is receiving many and handling multiple connections at a time. So for us, it's not so much of a big deal, and it does prevent on DOS attacks. So generally, it's a good thing. It's a good thing. So it does sound like TLS takes a lot of CPU energy, but realistically, like I said, it really doesn't. It did in the past, but it doesn't right now. CPUs were slow previously. TLS was or SSL really was quite heavy. Hardware accelerators were needed to speed it up on the server. And certificates were really expensive. Nowadays, client and servers can go ahead and handle these kind of cryptographic operations on the CPU completely fine. You don't really need hardware accelerators to go and do this. Google doesn't use them, or at least my information says Google doesn't use them. Certificates are very cheap or free in a number of cases now, and latency is most of the issue. So you still have this. I'm afraid that the big answer is that you can do some bits and pieces, but round trip times and network latencies really are still your big problem. Round trip times really are evil. And this is also, stated very nicely on his tlsfastjet.com, which I'm sure a lot of people have visited. And this is here, Adam Langley from Google, who works on a number of the standards that IETF said, on our production front-end machines, SSL or TLS accounts for less than 1% of the CPU load and less than 10 kilobits of memory per connection and less than 2% of the network overhead. And it's really nothing to go ahead and do this. So if you're stalling on upgrading to TLS because of performance, it's not really a good enough reason. Good enough reason is that it's a pain in the ass to set up, and we'll talk about that. So what can we do about these round trip times? We do want to get the round trip times down. So I did say we'd talk about how the spec is improving, and TLS 1.3 is something that's being worked on right now. TLS 1.3 is trying desperately to get these certificates down, to get these round trip times down. This is a TLS 1.3 handshake compared to the TLS 1.2. So as you can see here, so I add a few things to make it easier. We've gotten rid of the server key exchange and the client key exchange messages. Diffie-Hellman parameters and public keys are now sent in what we call a key share extension. So the server key exchange and the client key exchange is gone. It all happens now in the client hello and the server hello using the key share extensions. We're becoming even more extensible in TLS. The key share values were each consisting of some named elliptic curve Diffie-Hellman group and an ephemeral public key. I can't believe I said that right first time. That was bugging me today. If a server does accept the key exchange from the client, the server can then go ahead and respond, and then they can set up the master secret in a much quicker handshake. So this is actually only one round trip time, because in the finish you could go ahead and request your content as well. Do I want to tell you anything else about this? Yeah, that sounds good. Oh, just a quick note on the authentication. The Diffie-Hellman parameters itself aren't signed anymore. Authentication will be a little bit more explicit in TLS 1.3. There's a certificate verify message which gets sent. This is one round trip. That's great. We're happy with that. The abbreviated handshake is even more exciting. We got rid of our identifiers and tickets, so they don't really exist anymore, though something very akin to them does exist. We replaced those with pre-share keys. Pre-share key. I put a number of spaces there, so it would go onto a new line. So high tech, and it didn't work. So pre-share keys is defined on the previous connection and then reused on the abbreviated handshake. So centrally abbreviated handshake. So the abbreviated handshake looks like this. In the client hello, you send the key share and the pre-shared key. The pre-shared key has all of the information to go ahead and get the master secret from that we're using previously, and then you can go ahead and send data back and forth. That's still one round trip time, but can we do any better? So maybe. There is some work going on trying to create a zero round trip handshake. It has to be the second handshake. It can't be the first handshake. That would be impossible and incredibly insecure. This update is from the spec from November in 2015. It might have changed a little bit since then. So what happens here is at the end of the handshake, in the previous connection, a server sends server configuration message after the handshake, and it includes a number of things, including identifiers, some semi-static parameters, semi-static, whatever those things are called, and expiration dates, etc. So this then gets sent over in the client hello. There's the key share, including the early data, and the server is able to go ahead and use the server configuration to go ahead and respond and allow encryption to happen. But the key here is that the client hello is sent over some early data as well. So once a server has the key share, uses the server configuration data, they can go ahead and unencrypt the encrypted data that was in the client hello, which the client has understood from the server configuration information. It was able to encrypt it. And then they can go ahead, unencrypt it, and send the response to that data over in their server hello with their key share and any other information that they need to go ahead and do to set up the certificate. There's to set up the connection. There's a certificate verify there as well, if that's so necessary. This creates a 0 round trip time because we've got data going back and forth from the initial request. It's sort of a 0 round trip time. It's obviously it's still 1 round trip, but the TLS section of that is kind of built into the round trips that you're doing anyway. There are some caveats that this is sort of in-depth bits and pieces, but there's no server random. That means replay attacks are still possible on some of the data that you're sending in the early sending data. You might be able to do some replay attacks on just that early bit of data. This is mostly because 1 round trip time is still needed to get that ephemeral secret, that secret that can't be used over a number of different connections. So it does mean that there is this kind of attack vector there. And what people are doing to work on that is perhaps create APIs that go ahead and can mark certain pieces of information as replay safe. So maybe if you're on a banking website, the replay safe data would be a nice little picture of somebody taking out like money from an ATM or something, but not people's credit card details. So that's a situation that might happen. So yeah, that's pretty exciting, and lots more work is happening on that because it's a very important thing with lots of impacts. I wanted to gloss over Acme and Let's Encrypt really quickly because that's another thing that can help with the issues when it comes to certificates and certificate issuing and revoking. Probably people know about this before. Webmasters sometimes need a long time to create certificates and set them off. I did. It's a pain in the butt. You have to do a number of things you haven't done before, and it's wondrous that you still have to copy and paste stuff from one place over to another. I mean, it's crazy. People find it very difficult to go ahead and do. Yan Zhu from, I think she works at Brave now, but she worked at the EFF before, did a really cool presentation at DEF CON on this, where she asked her colleagues who also worked at EFF to set up HTTPS on the site, and you can just watch them squirm and do it. It's quite hilarious. These are security professionals. The old way of doing it, like I said, was a pain in the ass. You had to go ahead and do a certificate resigning request and copy and paste that data from a certificate authority into your web server, and then you have to do some kind of challenge to prove that you're in control of that web server. Either you get an email to that server, or you do some other thing like upload a file to it or something. All of these things seem like you're doing the same thing every time you have to set this up. So some clever people got together and thought this could be an automated method. We could do this in an automated way. And those people were working on Let's Encrypt, and which uses the Acme protocol, which is being also standardized at IETF. This is mostly they're trying to automate all of these types of things, issuing the certificate, revoking it, and other bits. And this is mostly done because on the web server, there's what we call a certificate management agent that goes ahead and does the things that the human used to go ahead and do. Acme generally just does 2 things. It does domain validation and certificate issuance and revocation, 3 things, let's say. The domain validation is very much what I described earlier. It's just the agents doing it, not the human. The agent on the web server will go ahead and create a key pair. It will prove to the certificate authority that it's in the possession of the private key. Then it will ask the CA, the certificate authority, which in most cases is going to be the Let's Encrypt, because Let's Encrypt's the only certificate authority using this right now, will then ask the agent to complete challenges. So it's not the user that's going, or the web developer or server admin that's being asked to complete challenges now. It's actually just the agent. So the agent would say, okay, cool, create this file on this server. I'll give you a nonce, encrypt that nonce, put that on that file, and then give me the location of that file, and then I'll read it. And this is just a protocol going back and forth. When the certificate authority gets that URL, they'll check that information is there with the encrypted nonce that they thought what they think it should be. And then they'll know that they can issue the certificate, or that the domain is valid. If you want some information on how a certificate issuance and revocation works on Let's Encrypt, I've included it here, but there's better information on the how does it work on part of their websites. Very good. So basically, then you can do nothing. Yeah. Oh, I just love this so much. Not either of those people, just this one GIF. So I don't want to talk about setting up TLS today because there's a lot of really good information on this out there. Super Soleil, who at Super Soleil on Twitter, Soledad Penedus, she has a fantastic blog for securing self-hosted websites with Let's Encrypt, so setting up websites with Let's Encrypt. If you have small websites with DigitalOcean, they have a couple of blogs as well about how to set up Let's Encrypt with their servers as well, using a bunch of different web servers, whatever you choose to use with them. There's lots and lots of ways that lots of advice to go ahead and do that. It's tricky to start off with, but you're done in the revocations instant, and you don't have that lag that your users may experience when revocation information starts to happen. So it was a long time, wasn't it? Yeah, it was a long time. Sorry, Perry. So we did talk about a lot of things. I hope you find it useful. We talked about public key crypto, TLS history, how TLS 1.2 works, the evilness of round trip times, how you could configure TLS to work for you, although perhaps you might not want to. One might think long and hard about that one. But also the good news about how TLS 1.3 is going to change, and how Acme and Let's Encrypt could go ahead and at least make certificates as part of the TLS section quite a little bit easier for you to work with. That's Super Soleil's Twitter account that you can go and find out her information to go ahead and work with Let's Encrypt. And now you can sleep. And thank you very much. Thank you. I'm sorry for it's so long. Do you want this? It was an hour and a half, or maybe 2. No, it was an hour and a half at home. So.
Did everybody get that? All right. Did everybody get Andrew? Is this one on? Yes, we are. All right. I hope you were all paying attention.
Oh,
I did put a tweet out during that, because the next LDNWebPerf Christmas quiz is going to be based solely on this presentation, right? And there's going to be about 500 questions in it.
That's awful.
Right?
You
it's
shouldn't do that.
Unbelievable. Right. So, I mean, what a fantastic talk. I think that, honestly, from me, I think that was one of the best talks we've ever had at the group. Right. So, really, thank you very much. I don't know how much of it is going to have actually sunk into my head come tomorrow morning, but like we said, we'll put the video will be online again, hopefully tomorrow, if I get a chance to do it that quickly. And the slides will be on the website.
Yeah, too. When I did some research for this, I mean, it's a very hard protocol to understand, and we're glad in a way that it's very hard to understand, because then it does make it harder to go ahead and crack. So, but there is a number of steps. It's not so easy as just understanding one thing. So yeah.
Cool. Right. So pizzas have not arrived yet. Right. Boo.
Well, that's good, because now I don't feel so bad.
So it means there's plenty of time for some questions. So has anybody got a question that wasn't like Jonathan straight in? There we go.
So how good are CDNs at optimizing the TLS performance?
So I mostly know about what happens on mobile networks, but I think that the theory is effectively the same. So they tend to operate as some of them operate as TCP optimizers. So you're because apart from with the keyless SSL method, you will have a TLS connection which ends from from your device, say perhaps to that content server, and then the content server over to the CDN, and then from the CDN over to the content server. So you've got this hop somewhere in the middle, which does impact the attack vectors, because if you're decrypting at any stage, and obviously you've got better attack vectors. But what they'll do at that point as well is because they're unencrypting at that point, or that's unencrypted data at that point, you've got a TCP optimization between the two of you, rather than having it through the whole process. So even if you are stopping between you and the CDN to go onto the content server, you've got an optimized TCP connection between you and that content server before going on. It's arguable whether that's actually better or not. Some people would argue that an end-to-end TCP connection is stronger than having it broken up into separate streams. Lots of people in the mobile operator place don't argue that. They say we need to break it up because of the way that mobile operator networks are so different compared to fixed. So it's just because you're not jumping through so many routers and so many different networks. Fried everyone's brain. Oh, hey.
What is the difference in the time taken for certificate authentication between
Oh, what certificate authentication? I'm not entirely too sure about that. It's something to go ahead and investigate. I would imagine if you're going ahead and using the same authentication method, then you're just dependent on the CPU, because you're not really dependent, because you're selecting an authentication method for your certificate here. So in the authentication method, we're going to use a certificate and we're going to authenticate that, but we're going to use RSA to go ahead and do that. And so we're using RSA on Android and an iOS device. Does it matter? It might matter more on the CPU than of the device rather than the operating system. Suppose it has an effect somewhere, but to be honest, I don't really know the answer to that question. Have you experienced there being differences?
Yeah, I know, I'm a bit lost in it, but I think it's something that I was advised that it might be something
Yeah, so another thing that I might take a look, well, that might be interesting to take, and maybe you've looked at it already, is on the Android devices, whether the certificate chain is complete. But I guess if you're doing loads of lookups, the certificate chain is complete. But when the client, whatever that client gets, let's say it's Chrome, goes ahead and gets the the certificate, and it goes ahead and tries to authenticate that, does it then does it have the full chain? Can it go all the way up to the original high level CA? If it doesn't, it might be sending another round trip to get that missing certificate from that certificate chain, and that might be where you're getting stuck. Possibly, I don't know. Yeah, so it'd be good. I mean, you can go ahead and dig in and find the cert somewhere, and then you can see if they're going to get the chain somewhere. And the other thing is, I guess you could look at the, if it's doing a revocation lookup. I don't know, Google does some amazing work. They sometimes make decisions on behalf of lots of people. So it sometimes is hard to understand exactly what's going on. Look, all of this stuff might be going over quick, and that might be your problem. You might be finding you found a quick bug, and that's it. Oh, really? The other way around? Okay, well, then you're stuffed because nobody's getting into Apple. I know a guy there, actually. Actually, no, do tell me, because this will make IETF really, really enjoyable to go ahead and talk to him about that. Okay, all right. Sorry about that. Andy?
Qualys is this SSL labs, SSL test.
Yeah.
Checking,
yeah, I did have that actually on one of the one of the graphs that was put together went through is Qualys SSL labs. Qualys SSL labs are going ahead and checking this stuff. There you go.
Yeah.
Yes, yeah, love you. Oh, such a great guy. Cool. Any other questions? Right, cool. Okay. Well, I guess be free to mingle and wait for the pizza and drink more beer and be reminded of the humidity of this country, which is really, really bad today. Come back from Japan and then it's really awful. But thank you so much, guys. I hope you find it useful. I'll clean up the slides and I'll send them out so that the people can distribute them. So I hope they're useful to you later down the line. Thank you.